Hello there, and welcome to the Sleepy History Channel. Tonight, we are stepping back into the Victorian era, a time when smoke curled above cities and iron began to move with purpose. This was an age that believed machines could solve problems, stretch possibility, and reshape the rhythm of everyday life. Steam breathed into engines. Gears turned thought into motion. Wires carried messages faster than any horse could run. The machines of the Victorian world were bold, ambitious, and sometimes unsettling. They dug deep into the earth, climbed across rivers, crossed oceans, and filled factories with sound and movement. They changed how people worked, how cities grew, and how time itself was measured. Many of the systems we rely on today were first imagined in this era, built with cast iron, brass, and remarkable confidence. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften, allow your breathing to slow, and give your thoughts permission to wander. Together, we will drift through an age of engines and ideas. Let's begin. Victorian steam engines turned coal into motion and remade daily life. In the early Victorian world, heat became a kind of muscle. A furnace turned water into pressure, and pressure pushed pistons that could lift, pull, spin, and grind for hours without tiring. Workshops that once depended on rivers could now run in the middle of a city, or beside a coal field, or near a busy port. Mills began to hum through the night. Mines reached deeper seams because pumps could fight flooding with steady power. Factories no longer had to wait for wind or weather. Engineers learned to treat steam with respect because a boiler could be a miracle one day and a menace the next. Out of that risk came standards, inspections, and new kinds of skilled work. The Victorian engine did more than power machines. It powered an idea that motion could be manufactured on demand. Railways stitched cities together with iron, timetables, and steam. A railway was a moving agreement between thousands of parts. Track had to be surveyed, graded, and drained. Bridges had to carry vibrating weight. Stations had to feed passengers into schedules that cared nothing for personal convenience. Once trains began running, distance felt different. A trip that once demanded a long coach ride and an overnight stop could become a morning departure and an afternoon arrival. Towns near the Line grew quickly. Towns left off the map often faded. Fresh food began to travel farther. Newspapers arrived on the same day, and ideas spread with them. Rail travel also introduced new risks. Speed meant collisions could be catastrophic, so signaling systems, disciplined rules, and standardized time became essential. The railway was not only transport. It was a machine for organizing a nation, one departure board at a time. Factory machines multiplied human effort and rewrote what work meant. A hand tool extends the body. A factory machine transforms it. Inside Victorian mills, power moved through shafts and belts that spun overhead like a mechanical ceiling. One engine could drive rows of frames, looms, and cutters all at once. That multiplication changed labor in complicated ways. Some jobs became less skilled because the machine held the technique. Other jobs became more skilled because maintenance and setup demanded knowledge and patience. Work rhythms shifted too. Instead of following daylight or seasons, the factory followed the clock. Noise became constant. Dust became a hazard. Safety guards were not automatic, and many people learned the hard way how unforgiving rotating parts could be. Yet wages, output, and availability of goods rose dramatically. Clothing, tools, and household items grew cheaper, and more uniform. The Victorian factory turned production into a system, and it trained society to live inside systems. The telegraph let news outrun horses, and it shrank the world overnight. Before electric messages, distance meant delay. A letter could take days to cross a country, and weeks to cross an ocean. Then a pulse on a wire began to carry meaning. Operators listened to clicks, translated patterns, and turned them into words that appeared in distant offices minutes later. Markets changed first. Prices could travel faster than goods, and traders learned to react to information instead of rumor. Railways changed too. Dispatchers could warn of trouble ahead and manage traffic with a new kind of coordination. Families felt the shift in a quieter way. A short line of text could bring relief or shock or reunion without waiting for the next ship. Cables pushed outward across seas, and engineers fought saltwater, storms, and broken lines on the ocean floor. The telegraph did not just speed communication. It taught society to expect immediacy. Victorian dynamos turned spinning copper into electricity for streets and homes. Electricity had long been a laboratory curiosity. The dynamo turned it into a practical output. When coils of wire moved through magnetic fields, current flowed, and flow could be managed. Early systems often began with bright arc lamps outdoors. They were intense and startling, and they made nighttime streets feel newly public. Power stations followed. They were filled with rotating machinery, hot air, and careful operators who watched gauges like sailors watch weather. Distribution created fresh problems. Wires had to be insulated, supported, and protected from damage. Switches and fuses had to prevent fires, and the public had to learn that a wire could bite without warning. Inside buildings, electric lighting began to compete with gas. It reduced soot and open flame, and it changed the feel of rooms after sunset. The dynamo connected motion to light, and that connection became a new kind of promise. Night could be engineered. Urban sewage pumps fought cholera with engineering, not prayer. Victorian cities grew faster than their waste systems. When people and refuse crowded together, disease found easy routes. Cholera outbreaks revealed a brutal truth. Water that looked ordinary could carry death. Engineers and reformers began to treat sanitation as infrastructure, not shame. Massive sewers were planned, and they needed pumping stations that could push foul water away from neighborhoods and into safer channels. These stations were often built with pride. Some were decorated like civic monuments, even though they housed grim work. Steam engines drove pumps that moved astonishing volumes hour after hour. The improvement was not instant, and debate was fierce. Yet cleaner water supplies and better waste removal steadily reduced outbreaks. The change also altered how cities smelled, how rivers looked, and how people thought about public responsibility. A sewage pump sounds unromantic, but it represents a turning point. Health became something a city could build, maintain, and protect. The printing press became industrial, and newspapers learned to roar. Printing once moved at the pace of careful hands. Victorian technology pushed it towards speed, volume, and urgency. Steam-powered presses could pour ink across type and roll paper through with relentless rhythm. That speed encouraged new kinds of journalism. Editors could publish more often. Reporters could chase stories that mattered today, not next week. Cheaper papers reached wider audiences, and reading became a daily habit for many people who had never owned books. Illustrations and later photographs added a new authority to the page. With circulation came influence. Newspapers helped shape elections, public reforms, and popular fears. They also created a shared sense of events. A strike, a shipwreck, a court scandal, and a discovery could become common conversation across a whole city. The press was not only a machine for ink, it was a machine for attention. It trained societies to look outward, to react quickly, and to feel connected through shared headlines. Steamships stopped fearing wind, and oceans became scheduled routes. Sailing ships were elegant, but they negotiated with weather. Steamships changed that relationship. With engines below deck and coal in the bunkers, a captain could plan a crossing with far more certainty. Routes became timetabled. Mail became more reliable. Passengers could book voyages with expectations that sounded almost modern. Steam also changed global trade. Perishable goods had a better chance of arriving in usable condition. Manufactured items could move on steadier schedules. Ports adapted with new coaling facilities, and ship design evolved to carry both cargo and fuel efficiently. The sea was still dangerous. Boilers demanded careful management, and mechanical failure far from land could become a nightmare. Even so, confidence grew. Steamships helped shrink the psychological size of the world, not just the travel time. They carried migrants, tourists, soldiers, and ideas across oceans in patterns that repeated week after week. The wind did not disappear, but it stopped being in charge. The beam engine powered mines, pumping water from deep underground. In many mining districts, the most feared sound was not a cave-in. It was the slow rise of water. A walking beam engine answered that fear with a simple drama. A great pivoting timber or iron beam rocked back and forth, driven by a steam cylinder on one side and a pump rod on the other. Down in the shaft, the rod worked like a piston in a giant syringe, lifting water step by step toward daylight. Engine houses were built like fortresses because the machine mattered as much as the mine itself. Operators listened for changes in rhythm that could warn of trouble, and they learned to treat valves and seals with respect. When the pump kept going, miners could chase ore bodies that was unreachable for centuries. The beam engine turned depth into a solvable problem, and it made whole landscapes worth digging. The Cornish engine saved fuel by squeezing more work from steam. Coal cost money, and hauling it to remote mines could cost even more. In Cornwall, engineers began to treat every puff of steam like a precious coin. Their solution was a pumping engine that worked in deliberate strokes. Steam filled the cylinder, then it was shut off early. After that, the trapped steam expanded, pushing the piston for the rest of the stroke without extra fuel. Condensing the steam afterward created a partial vacuum, which helped pull the piston back and improved efficiency. These engines became famous for performance trials, where results were recorded and compared, and pride was on the line. A well-tuned machine could do astonishing work on surprisingly little coal, and owners paid close attention. Efficiency also meant endurance. Mines could keep pumping through hard times instead of shutting down when costs rose. The Cornish engine shows a Victorian obsession that still feels modern. Waste was not just untidy. Waste was failure. Compound steam engines expanded steam twice and sailed farther on less coal. A simple engine asks steam to do its work in one place. A compound engine asks it to work in stages, like a traveler who keeps finding fresh tasks before resting. High-pressure steam first pushed a small cylinder, then the partially used steam flowed into a larger cylinder where it expanded again. The same heat delivered power twice, and the machinery ran with less strain than forcing everything through one violent step. On ships, this mattered deeply. Coal took space that could have held cargo, and every extra ton meant less profit or less range. With compounding, vessels could steam longer between coaling stops, and routes that once felt risky became routine. Engineers also liked the smoother running and reduced wear, which meant fewer breakdowns at sea. The compound engine did not feel like a flashy invention. It felt like a clever conversation with physics, and the ocean listened. Triple expansion engines pushed ocean liners into a new era of speed. When engineers added a third stage, the ship's engine room became a cathedral of motion. Steam arrived hot and pressurized, and it worked through 3 cylinders of increasing size. Each stage extracted more energy, and less heat was thrown away. That efficiency translated into real choices. A liner could carry more passengers in comfort, or more cargo for profit, or simply push for higher sustained speed on long runs. The rhythm of travel changed. Crossings became dependable, which reshaped mail, business, and even the feeling of separation between continents. Down below, the work was intense. Stokers fed furnaces, engineers watched gauges, and the whole space pulsed with heat and sound. A failure in that environment could be deadly, so training and discipline mattered. Triple expansion engines were not only powerful, they were persuasive. They convinced people that an ocean could be treated like a route with a timetable, and that belief helped build the modern world. Early submarines proved underwater travel was possible, even if terrifying. The Victorian imagination loved the sea, yet it also feared what lay beneath it. Early submarines brought that hidden world into engineering. Designers had to solve problems that sound simple until you try them. How do you breathe when the air is trapped? How do you see when the water blocks light? How do you control depth without sinking forever? Some craft used hand cranks or early engines. Some relied on ballast tanks and careful trimming, and nearly all demanded nerve from the crew. The interior could be cramped, dim, and heavy, with the awareness that water presses from every side. Yet the achievement mattered. These experiments showed that a vessel could be controlled below the surface, not merely lost. Navies paid attention, inventors took notes, and the concept began to feel less like fantasy. Early submarines were not yet comfortable or reliable. They were proof of principle, and proof can change history. Torpedoes turned small boats into serious threats against big ships. For a long time, size felt like safety at sea. Bigger ships carried more guns, thicker armor, and more crew. The self-propelled torpedo challenged that assumption. A compact weapon could travel through water toward a target, driven by stored energy, guided at first by simple mechanisms and later by better control. Suddenly, a small, fast craft could threaten a massive vessel, and navies had to rethink strategy. New defenses appeared, including nets, patrol boats, and different formations. Ship design shifted too. Compartments and improved pumping systems mattered more because damage control could decide survival. The psychological change was just as important. Commanders could no longer assume that distance from shore or superiority in tonnage meant protection. A hidden approach could be enough. This did not make the ocean safe. It made it uncertain in a new way. The torpedo is a classic Victorian lesson. A machine can compress power into a small package, and that compression can reshape balance faster than tradition expects. The transatlantic cable made diplomacy faster, and mistakes more immediate. Before a reliable cable, governments had time to breathe between messages. Ships carried letters, and delay created space for reconsideration. The transatlantic cable changed that rhythm. Suddenly, leaders could exchange instructions and reactions in hours instead of weeks. That speed could prevent misunderstandings, but it could also amplify them. A hastily worded message could provoke a response before cooler heads had time to intervene. Newspapers felt the change as well. International news could reach readers quickly, which increased public pressure on decision-makers. Trade benefited from faster information, yet markets also became more sensitive because rumors could spread rapidly and trigger quick decisions. The cable did not remove distance, but it reduced its cushioning effect. Diplomacy became more immediate, and immediacy can be both clarity and danger. This is one of the most fascinating consequences of Victorian machines. They altered not only what people could do, but how people had to behave. When communication accelerates, patience becomes harder to practice. The transatlantic cable helped create a world where reaction time mattered, and where words could have consequences while the ink was still fresh in someone's mind. The screw propeller beat paddle wheels in rough seas. Paddle steamers looked confident on calm water, but waves could make them awkward. A paddle wheel can rise and fall with the swell, so one moment it bites hard, and the next it slaps air. A screw propeller stays underwater and keeps pushing, even when the sea is restless. That single change transformed ship design. Propellers allowed narrower hulls, better balance, and engines tucked safely below the waterline. They also protected the means of propulsion. A paddle wheel is exposed and easy to damage in storms or combat, while a propeller is hidden like a clenched fist under the surface. Early adopters faced skepticism because the idea felt strange. How could a spinning screw in water outperform those huge visible wheels? Then, trials and voyages answered the question. Ships with screws handled heavier seas with steadier speed, and navies noticed quickly. The propeller did not just move ships. It moved confidence, from fair weather to all weather. Ironclad warships wrapped timber navies in metal skin. For centuries, naval power meant wooden walls, canvas, and cannon. Then armor arrived, and the old logic cracked. Ironclads carried thick plates that could shrug off shots that would have shredded a traditional hull. Suddenly, a fleet built for one era could feel obsolete in a single season. The change altered tactics at sea. Ramming returned as a frightening possibility because armored bows could survive impacts. Guns grew heavier, and engineers began a race between penetration and protection. Ironclads also demanded industry. Building them required large rolling mills, skilled riveting, and reliable engines, and not every nation could keep up. Life aboard changed too. Metal hulls could become ovens in sunlight and condensation traps in cold weather, so ventilation and design became matters of survival. An ironclad was a warship, but it was also a statement. It said that warfare had entered the age of machines, and tradition could not vote its way out. The Bessemer process demanded careful chemistry, or steel turned brittle. The new converter could make steel quickly, but speed did not forgive ignorance. Blowing air through molten iron burned away carbon and other impurities, and that roaring reaction looked like certainty. Yet the details mattered. Some ores carried phosphorus, and if it stayed in the metal, it could make the final product weak and unreliable. A rail that cracks or a plate that snaps is more than a defect. It is disaster waiting for a load, a storm, or a sharp impact. Early steelmakers learned that good metal began long before the converter. It began in the choice of ore, the control of temperature, and the timing of the blow. They also learned to adjust composition afterward by adding carbon back in careful amounts. This was chemistry practiced at industrial scale, with red-hot consequences. The process pushed metallurgy into a new professional world, where measurement and material science became as important as muscle and fire. Open hearth furnaces offered slower control and steadier steel. Some problems cannot be rushed, and steelmaking is one of them. The open hearth furnace traded speed for control. It used intense heat reflected within a wide chamber, and it allowed workers to watch, sample, and adjust the melt over a longer period. That patience made a difference for quality. Scrap steel could be recycled into the charge, which appealed to factories that produced offcuts and rejected parts. Producers could tune carbon content and reduce unwanted elements with more confidence, which meant fewer unpleasant surprises in finished beams and plates. The work still demanded skill. Heat shimmered above the hearth, and the environment punished mistakes quickly. Yet the slower pace created room for judgment, and judgment created trust. When a bridge engineer or shipbuilder needed metal that would behave predictably, that predictability was worth extra time. The open hearth furnace represents a Victorian shift from spectacle to discipline. It suggests that progress is not only faster machines. Sometimes it is better control. Rolling mills flattened red-hot metal into rails and plates. Imagine a glowing slab of metal moving like bread dough through enormous turning rollers. That is the rolling mill, and it changed what industry could build. Instead of casting every shape, makers could form long, consistent sections with precise dimensions. Rail production became a signature task. A rail must be uniform because wheels punish every bump, and a flaw can become a break. Rolling also produced plate steel for boilers, ship hulls, and bridges, and those plates needed dependable thickness to handle stress. Mills demanded coordination. Heating furnaces prepared the metal, then teams guided it through the rollers with practiced timing. As the piece stretched and thinned, it cooled quickly, so delays could ruin a run. The scale was mesmerizing and dangerous. A slip could injure or kill. Yet the output was transformative. Rolling mills did not only shape metal, they shaped infrastructure, giving the 19th century the long, straight components it needed to expand railways, shipyards, and cities at once. Riveting crews built bridges and boilers with hammer rhythm and skill. Before welding became common, riveting was the sound of construction. A rivet began as a short metal pin heated until it glowed. One worker placed it through aligned holes in plates or beams, another held a heavy tool on the far side, and others hammered the exposed end into a tight head. As the rivet cooled, it shrank slightly and clamped the pieces together with fierce grip. A good crew moved like a practiced ensemble. They had to coordinate timing, heat, and force, often in cramped spaces or high above the ground. Bridges depended on their accuracy because vibration and load would punish any weakness. Boilers depended on it even more because pressure seeks every escape. Riveting was not only strength, it was inspection. A Paul rivet could be heard by its sound under a hammer and replaced before it failed. These crews built the skeleton of the industrial age, one glowing pin at a time. Precision lathes made identical parts and launched modern mass production. A lathe looks simple. It spins material and lets a cutting tool shape it. In Victorian hands, that basic idea became a path to sameness with astonishing accuracy. Better bearings reduced wobble. Better cutting steels held sharp edges longer. Measuring tools became trusted, so a worker could aim for a standard instead of a personal best guess. When parts could be made to match, machines could be repaired faster. A broken piece no longer required a custom replacement made by the original shop. It could be swapped for another that fit. That change rippled outward. Armories pursued interchangeable components for weapons. Railways demanded consistent fittings for rolling stock. Factories depended on replacement parts to reduce downtime. Precision also fed invention. Designers could imagine mechanisms with tight clearances because workshops could actually build them. The lathe did not just shape metal. It shaped the logic of manufacturing, where sameness became a feature, not a flaw. The Bessemer converter made cheap steel, and changed skylines and ships. For centuries, steel could be excellent and expensive at the same time. Then a new approach turned iron-making into a dramatic performance. A Bessemer converter blasted air through molten metal, and the impurities burned away with roaring flame. The process was fast, and speed meant cost dropped. With more steel available, engineers began to think bigger. Rails could be tougher, so trains could run heavier loads with fewer brakes. Bridges could span wider gaps with slimmer structures. Shipbuilders could move beyond traditional materials and build stronger hulls for rough seas and long voyages. Steel also reshaped cities. Taller frames became possible, and architecture started to reach upward with new confidence. The new metal still demanded care. Composition mattered, and early batches could fail if chemistry was ignored. Even so, the converter helped turn steel from a luxury into a foundation. It gave the Victorian era a new skeleton. The steam hammer shaped huge metal pieces with a single controlled blow. In a Victorian forge, this machine could do what a whole crew of sledgehammers could not. A glowing shaft, an anchor link, or a crank for a ship's engine could be placed beneath a massive falling head, then shaped with repeated strikes that landed exactly where the bore Smith wanted. The secret was control. Power came from steam, but the blow could be light as a tap or heavy enough to make the ground shiver. That meant delicate work and brutal work could happen on the same floor. It also meant large parts could be made in one piece, which reduced weak joints and saved precious time. Observers described the scene with awe because it looked like industry had learned to punch with precision. The steam hammer helped turn heavy engineering from heroic improvisation into reliable production, and it made ambitious designs physically possible. The planing machine shaved metal flat, making true surfaces possible. If two parts do not meet cleanly, the whole machine becomes a compromise. The planer attacked that problem with patience and force. A workpiece was clamped to a moving table, then slid back and forth under a fixed cutting tool that peeled away thin layers of metal. Each pass removed only a little, but the result could be a surface so flat it felt unnatural to anyone used to hand filing. This mattered for engine frames, slideways, and large mating faces where wobble and vibration could ruin accuracy. It also changed how builders thought. When flatness became achievable, designers could demand tighter fits, smoother motion, and better sealing. Planers were often enormous, with tables long enough to carry castings that looked like sections of bridge. The machine itself became a symbol of discipline. It did not rely on a craftsman's mood or a lucky day. It relied on repeatable motion and careful setup and time. The milling machine cut complex shapes and unlocked interchangeable parts. A drill makes a hole, and a lathe makes a cylinder. Milling could do far more. A rotating cutter could travel across a block of metal and carve slots, deers, T-ways, and intricate profiles that previously required slow handwork. That freedom mattered because it let factories make parts that matched drawings, not just other parts made by the same person. Once shapes could be produced consistently, repair and assembly changed. A damaged component could be replaced without weeks of fitting, and a machine could be built from stock pieces rather than custom puzzles. Milling also fed new industries that demanded precision at scale, including sewing machines, bicycles, and the tools that built other tools. Workshops began to feel like laboratories where metal could be persuaded into almost any geometry. The milling machine turned complexity into something that could be scheduled, ordered, and repeated, and that shift quietly underpinned the Victorian appetite for mechanisms. The turret lathe sped repetitive work, turning factories into time machines. This lathe was designed for sameness, and it treated repetition like an advantage. Instead of stopping to swap one cutting tool for another, a worker could rotate a turret that held several tools ready to go. Drill, bore, face, and turn could follow in quick succession, with fewer pauses and fewer chances to lose alignment. In a shop making hundreds or thousands of similar pieces, those saved moments piled up into an astonishing increase in output. It also changed the feel of labor. Skill still mattered, but the rhythm became steadier, like playing a well-rehearsed sequence. Foremen could predict production with new confidence, and orders that once took weeks could be filled far sooner. The turret lathe helped factories supply railways, engines, and household goods without constant reinvention. It made a kind of mechanical momentum, where yesterday's setup could carry straight into tomorrow's work, and consistency became the heartbeat of the floor. Gauge blocks and micrometers made almost right suddenly unacceptable. Victorian industry discovered a sharp truth. If you cannot measure precisely, you cannot truly control what you make. The micrometer let a worker feel tiny differences through a turning thimble, while gauge blocks provided trusted lengths that could be stacked to create standards on the bench. With these tools, arguments changed. A part was not judged by eye or by pride. It was judged against a number, and the number could be checked again. This altered everything from engine bearings to machine slides, because better fits meant less vibration, less waste heat, and fewer mysterious breakdowns. It also changed training. Apprentices learned that careful measurement was not fussiness. It was power. Once tolerances became part of daily speech, factories could share specifications across towns and even across countries. The measuring tools were small enough to hold in one hand, but they helped build bridges, locomotives, and ships that depended on accuracy no one could see. Standard screw threads let bolts fit anywhere, not just one workshop. Before standards, a bolt was often married to its nut for life. Different shops cut threads with different angles and pitches, so a fastener that worked in one factory could be useless in another. When thread forms became standardized, a quiet miracle arrived. Repairs became simpler, and supply chains began to function with less confusion. Railways could stock fewer varieties of spares. Shipyards could order fasteners with confidence. Engineers could design assemblies knowing that replacement parts would actually join together without hand-fitting. Standard threads also improved safety, because a properly matched bolt and nut could hold predictable loads instead of failing from poor engagement. This sounds mundane until you imagine a bridge crew high above a river or a locomotive shop working against a timetable. Standardization saved time, money, and sometimes lives. It also changed the culture of manufacturing. It rewarded shared rules over private habits, and it helped turn Victorian mechanics into a connected industrial world. Hydraulic presses squeezed metal with calm force, not swinging hammers. Where a hammer strikes, a press persuades. Victorian hydraulic presses used fluid pressure to deliver enormous force smoothly, and that smoothness opened new possibilities. Metal could be formed, straightened, or compacted without the shock that could crack castings or distort delicate sections. Presses could bend thick plates for ship hulls, shape parts for railways, and compress materials into dense blocks for transport. The principle felt almost magical. A relatively small pump could create massive pressure in a larger cylinder, and the operator could control it with levers and valves. That made the machine feel powerful, but also precise. It could pause mid-stroke, then continue, which gave workers time to align pieces and correct errors. In an era of loud impacts and flying sparks, the hydraulic press offered a different kind of strength, one that arrived quietly but relentlessly. It helped industry move from brute force toward controlled forming, and it changed what could be shaped safely. Steam-powered cranes lifted weights that once demanded whole teams. A heavy lift used to mean ropes, pulleys, and many exhausted hands. Then steam power climbed into the skyline. A crane with a steam engine could raise iron beams, boilers, and stone blocks with steady authority, and it could swing them into place with less shouting and less chaos. Ports, rail yards, and construction sites began to look different. Tall masts and jib arms became common, and projects grew bolder because moving large pieces was no longer the hardest part. This also shifted responsibility. A single operator at the controls could do the work of many, and a mistake could be catastrophic. That pressure encouraged better brakes, clearer signals, and stricter site discipline. Steam cranes helped make large-scale building practical, from bridges to stations to new factories. They also made cities feel like they were assembling themselves, piece by piece, with machinery acting as the muscles of expansion. When a Victorian crane lifted a load, it was not only moving weight, it was moving ambition. Dockside steam winches made loading ships faster and far safer. At a busy dock, time was money, and delays could ripple across trade routes. Steam winches brought speed and order to the messy business of cargo. With a powered drum and stout cables, a crew could hoist crates, barrels, and machinery from a hold, then lower them onto the quay with controlled tension. That control mattered because uncontrolled loads swing, and swinging loads injure people. Winches helped reduce the chaos of manual hauling, and they made it possible to move heavier goods that would have been almost impossible to shift quickly by hand. They also changed scheduling. Ships could turn around faster, which meant more voyages per year and fresher deliveries. The dock became a choreography of ropes and signals, and the winch was the steady heartbeat that kept it moving. In a world that depended on maritime trade, a faster dock was not a convenience. It was a transformation, and steam made it happen. Steam dredgers moved rivers and harbors, reshaping coasts by machinery. A harbor is never finished, because water keeps carrying sand and silt. Victorian engineers met that constant change with dredgers, floating machines that could scoop or suction material from the bottom and move it elsewhere. Steam power drove buckets, pumps, and rotating cutters, and the result was a new ability to deepen channels and extend ports. This mattered for the largest ships, which needed greater draft and safer approaches. It also mattered for cities, because a prosperous port could feed factories with raw materials and export finished goods. Dredging could even alter shorelines by building up land with the removed spoil, turning mud into new space for docks and warehouses. The work was gritty and relentless. Machinery groaned, chains clattered, and crews battled tides and storms. Yet the outcome could feel almost impossible. A shallow river could become a shipping route. A small harbor could become a gateway to the world. Dredgers did not just clear water. They redrew maps. The locomotive's firebox was a moving furnace on wheels. To understand a Victorian train, picture the heat first. Inside the firebox, coal burned on a grate with air rushing through, and the metal walls glowed with stored energy. That heat boiled water in the surrounding boiler, and the steam drove pistons that turned wheels through rods and cranks. The machine looked solid from the platform, yet it was always balancing forces. Too little draft, and the fire sulked. Too much, and it roared, throwing sparks that could set dry fields alight. Crews learned to read the color of the flame, the pull of the exhaust, and the sound of the engine under strain. Every mile was powered by thousands of small decisions, shovel by shovel. Passengers might feel only speed and wind at the window. The crew felt a furnace that had to be fed, watched, and respected. The Stephenson rocket showed how design could tame steam speed. Early locomotives could be stubborn creatures. They slid, steamed poorly, and wasted heat. The rocket became famous because it treated speed as an engineering problem, not a dare. Its boiler used many small tubes to expose more hot surface to water, which helped make steam faster. Its exhaust was directed up the chimney, which pulled air through the fire and kept combustion lively. Weight distribution and wheel arrangement were considered carefully, because traction mattered as much as power. The result was a locomotive that did not merely move. It performed predictably, which is what railways needed most. When the public saw that predictability, a new kind of trust appeared. People began to believe that a machine could keep an appointment. That is a quiet revolution. The rocket helped turn rail travel from spectacle into system, and systems are what reshape a century. The expansion of railways created time zones, and clocks became law. Before railways, local time could be personal. Noon was when the sun stood highest where you lived, and the difference between towns barely mattered. Trains made that impossible. A timetable cannot argue with a church clock that runs 8 minutes behind, and a missed connection can ripple across an entire line. Railway companies began to adopt standard time, and stations displayed it with confidence. Soon factories, post offices, and city streets followed. Clocks became tools of coordination, and lateness became measurable in a new way. This change reached into ordinary habits. Work shifts aligned. Meetings began on the minute. Even leisure learned to obey the dial. It also changed how people imagined the country. Places felt closer because they shared a schedule, and shared time creates shared reality. The Victorian clock was no longer only a household object. It became a public rule, enforced by wheels and whistles. The Westinghouse air brake helped trains stop with confidence. Early trains could go fast, but stopping was a tense negotiation. Brakemen sometimes climbed onto moving cars to turn hand wheels, and they did it in rain, smoke, and darkness. An air brake system changed the meaning of control. Compressed air could send a command down the whole train. So many brakes engaged together instead of one at a time. That meant shorter stopping distances, smoother halts, and far fewer terrifying moments when a heavy train refused to slow on a grade. It also changed the human story. The job became less deadly, and the crew could focus on signals and track rather than survival on the rooftops. Passengers felt the difference too. A controlled stop is a kind of comfort, even if you never think about it. Better braking allowed heavier trains and tighter schedules, which pushed railways toward modern scale. Sometimes an invention does not make you faster. It makes you safer at speed, and that can change everything. Block signaling reduced collisions by turning track into managed space. A single track line can feel like an open road until two trains meet. In the early days, timing and trust did much of the work, and mistakes could be catastrophic. Block signaling introduced a new idea. The line was divided into sections, and each section had rules about entry. Signals could warn a driver to slow, stop, or proceed based on whether the block ahead was occupied. This changed the landscape. Posts, lamps, and later semaphores became part of the railway's language, and crews learned to read that language without hesitation. It also changed responsibility. Decisions moved from guesswork in the cab to coordinated oversight along the route. Trains could run closer together with less risk, which increased capacity without adding new rails. The system did not remove danger, but it reshaped it into something that could be managed. A block signal is simple to look at. Behind it sits a philosophy that the future can be made safer by dividing it into knowable pieces. Telegraph lines followed railways, giving dispatchers a new kind of sight. Alongside the track, poles marched across fields and through cuttings, carrying wires that seemed almost weightless. Those wires gave railways a nervous system. Stations could report departures, delays, and trouble ahead, and dispatchers could respond in minutes instead of hours. A broken axle, a fallen tree, a stalled freight, all of it could be described and acted upon before it turned into a collision. This also changed the social texture of travel. Small towns along the line became nodes of information, not just places to take water or coal. Operators listened to the clicking instrument, then wrote words that could alter the movement of tons of steel. The coordination was invisible to passengers, yet it shaped every arrival. It also introduced new vulnerabilities. Storms could snap wires, and sabotage could cut communication, so railways learned to build redundancy and discipline. The telegraph made dispatching feel almost like strategy, where knowledge arrived before the train did. The Underground Railway proved cities could move people below streets. Victorian streets could be crowded, muddy, and loud, with carts, horses, and pedestrians all competing for space. Building a railway beneath that chaos sounded impossible, yet it happened. Tunnels had to be dug, supported, and kept from collapsing under buildings and roads. Stations needed stairways, platforms, and ventilation, because smoke and steam do not behave politely underground. At first, the experience could be harsh. Air was thick, lighting was dim, and the idea of being sealed below the city challenged the nerves of many riders. Still, the promise was irresistible. Travel times became more reliable, and whole neighborhoods felt nearer to work and markets. The Underground Railway also changed the way people imagined a city. It suggested that streets were not the only surface for movement. Layers were possible. Once that idea took hold, it became easier to picture subways, utility tunnels, and the hidden infrastructure that supports modern life. The Victorian Underground was more than transport. It was a new dimension. Cable-hauled streetcars climbed hills where horses would fail. Some streets were simply too steep for horse-drawn cars, and steam engines in dense neighborhoods brought noise and smoke that people did not want. Cable traction offered a clever workaround. Beneath the street, a continuously moving cable ran through a slot between the rails. The car had a grip mechanism that could clamp onto the cable to move, then release it to coast or stop. Power came from a stationary engine house, which meant the car itself could be lighter and cleaner. This system demanded precision. The cable had to run smoothly around pulleys, and the grip operator needed timing and strength to engage without jolting passengers. When it worked, the effect was magical. A car could climb grades that would exhaust animals, and it could do it with steady confidence. Cable streetcars also changed streetscapes, adding slots, vaults, and maintenance access that made the city feel engineered from the ground up. It was transit that relied on hidden motion, like a city with a heartbeat under its pavement. Steam road rollers flattened streets, making cities cleaner and quieter. A rough road is more than uncomfortable. It shakes wagons apart, slows deliveries, and turns rain into ruts that breed mud and filth. The steam road roller attacked that everyday problem with weight and repetition. Its heavy cylinders compressed layers of stone and gravel, and the result was a surface that held together under traffic. That change had surprising consequences. Smoother roads reduced the clatter of wheels, which softened the constant noise of busy streets. They also cut down on dust that once rose in clouds during dry weather, and the dust found its way into lungs, shops, and food. Better road surfaces helped new forms of travel too, from safer cycling to early motor traffic that would have been miserable on broken ground. The roller itself became a familiar sight, moving slowly, steaming gently, leaving behind a visible difference that people could feel underfoot. It was a machine that improved life without needing a grand monument, and that is part of its quiet power. The safety bicycle gave ordinary people speed, freedom, and distance. For many riders, the high-wheeler was thrilling and intimidating because a fall from that height could be brutal. The safety bicycle changed the bargain. With two wheels of similar size and a more stable riding position, it offered mobility that felt achievable for far more people. That widened access mattered socially as much as mechanically. Commuting became possible without a horse. Short trips turned into longer ones, and countryside roads opened up to weekend travel. Bicycles also nudged towns to improve surfaces, because a smooth road benefits everyone who moves through it. Repair shops and cycling clubs appeared, and they created a culture of tinkering that fed later industries. The bicycle taught people to think in gears, bearings, chains, and efficient motion, and it made mechanical literacy part of ordinary life. It also shifted expectations. Once you have traveled 10 miles under your own power, a city feels smaller, and your world feels wider. The safety bicycle did not only carry bodies, it carried independence. Chain drive made bicycles efficient and changed how legs met wheels. The earliest popular bicycles often drove the front wheel directly, so speed depended on wheel size. That is why some riders perched so high above the road. Chain drive rewrote that relationship. Your feet could turn a small chainring. The chain could carry that motion to the rear wheel, and gears could multiply the effect. Suddenly, a bicycle could be fast without being tall, and it could be stable without feeling sluggish. This was not only comfort. It was engineering you could feel in your bones. Hills became negotiable instead of humiliating, and long distances became plausible for ordinary riders. The chain also made design more flexible. Frames could be shaped for strength and balance, not for the awkward geometry of direct drive. Workshops sprang up to produce sprockets, chains, and precise tooth profiles, and those tiny parts demanded accuracy that pushed toolmaking forward. A simple loop of metal links helped turn cycling into a practical revolution. Pneumatic tires softened roads and made cycling feel effortless. A hard wheel on a rough road wastes energy in 1,000 little jolts. Early riders knew the feeling in their wrists and teeth. Pneumatic tires changed the ride by trapping air, which works like a spring that absorbs bumps instead of throwing them back at you. Comfort was only the beginning. With less vibration, wheels kept better contact with the ground, and that improved control. Rolling resistance also dropped, so the same effort carried you farther. People began to treat cycling as something they could do for pleasure, not only for grit. The tire created new industries as well. Rubber had to be sourced, processed, and shaped. Valves had to hold pressure reliably. Repair kits became everyday items, and punctures became a new kind of roadside problem to solve. Roads themselves felt the influence. When enough citizens start caring about smooth surfaces, city councils start listening. A cushion of air helped turn movement into joy, and joy into demand. Early motor cars borrowed bicycle parts before engines found their own style. The first motor cars did not arrive as a complete new species. They arrived as hybrids. Builders reached for what already worked, and the bicycle industry was full of light frames, ball bearings, chains, and clever steering ideas. Many early vehicles used familiar components, then added an engine that behaved like a restless animal. Suddenly, the challenge was not only making power, it was coping with it. Bearings needed better sealing. Frames needed stiffness. Brakes needed to tame more speed and more mass. Even the idea of a driver's position had to be invented, because a motorcar was neither carriage nor bike. Workshops that had made cycles found themselves supplying parts for an entirely new market, and the skills transferred quickly. Precision machining, reliable fasteners, and lightweight construction all mattered. This borrowing also shaped culture. The motor car began life as a machine for tinkerers, not corporations. It carried the bicycle's spirit of experimentation into the age of engines, and it made the road feel like a workshop. Traction engines pulled heavy loads, turning roads into slow railways. On a country road, a traction engine looked like a factory that had decided to travel. Huge wheels, a tall chimney, and a boiler that hissed with purpose. It could haul wagons, timber, and machinery that would overwhelm teams of horses. For farmers and contractors, this was transformative. A heavy threshing machine could be moved from field to field. Stone and gravel could be hauled for road building. Logging became more systematic. The engine also demanded new habits. It needed water stops. It needed fuel. It needed a driver who understood pressure, traction, and the dangers of steam. Roads were tested by the weight, and some places responded with stronger surfaces and better bridges. Communities also responded with awe and anxiety, because a traction engine could be loud, smoky, and intimidating. Yet it proved a powerful idea. If you can bring the engine to the job, you can expand what the job can be. It was a step toward modern construction equipment and a reminder that mobility can be industrial. Portable steam engines powered farms wherever the belt could reach. A portable steam engine was a clever compromise between fixed power and roaming power. It could be hauled into a farmyard, chocked in place, and then connected by a long belt to whatever needed turning. One day it might drive a threshing machine. Another day it might run a saw, a pump, or a grinder. The engine became a visiting heart that could energize different tools without each tool needing its own power source. This changed the rhythm of rural work. Tasks that had relied on many hands could be finished faster, and some jobs could be scheduled around weather windows with greater confidence. The scene was vivid. The belt whipped in a steady loop. The flywheel spun. The exhaust puffed like breath in cold air. It also demanded skill and caution. Belts could snag clothing, and boilers required careful attention. Still, the portable engine brought the logic of the factory into the countryside, and it did it without permanently reshaping the farm's buildings. It was industrial power on a temporary lease. Mechanical reapers cut grain fast, shrinking the need for field labor. Harvest is a race against time. Grain must be cut when it is ready, and storms do not wait. Mechanical reapers changed that race by turning cutting into a controlled sweep. A set of blades moved back and forth, and a reel guided stalks into the knife so they fell in a clean line. One machine could do the work of many people with scythes, and it could keep going when arms would tire. This had social consequences that reached far beyond the field. Large farms could expand acreage. Labor needs shifted from seasonal crews toward machine operators and mechanics. Timing improved, which reduced losses and helped stabilize food supply in many regions. The reaper also encouraged standardization in farming. You needed fields laid out for machines, not for footpaths. You needed repairs on demand, not after a day's rest. Even the sound of harvest changed. The whisper of blades gave way to a metallic rhythm, and the field began to feel like an outdoor workshop. The reaper made speed a tool, and it made time the main opponent. Steam threshers separated kernels at scale and made harvests decisive. Cutting grain is only the beginning. The real work is separating edible kernels from straw and chaff. A steam thresher turned that messy process into a roaring, purposeful sequence. Bundles went in. Drums beat and shook the stalks. Sieves and airflow sorted the grain, and the clean result poured out like treasure. What once took long days of hand flailing and careful winnowing could now happen with astonishing throughput. This changed rural economics. A traveling threshing crew could move from farm to farm, and neighbors might coordinate schedules like a shared festival of machinery. The machine also demanded planning. Fuel and water had to be available. Belts had to be aligned. Everyone had to respect moving parts that could grab an arm in an instant. Dust filled the air, and the work was loud, yet it was also exhilarating. When the thresher ran well, the harvest felt secure. The grain was no longer a fragile pile waiting for weather. It became a stored result. Steam threshing did not only speed the farm, it reduced uncertainty, and that can feel like a kind of wealth. Cotton gins and carding machines fed mills with relentless appetite. Victorian textile power depended on an earlier transformation, the ability to prepare fiber faster than hands could manage. The cotton gin removed seeds from cotton, turning a slow chore into rapid processing. Carding machines then took clumps of fiber and combed them into a soft, aligned web ready for spinning. Together, these machines created a steady stream of material that could keep large mills busy all day. That flow changed entire regions. Cotton agriculture expanded. Transport networks adjusted to move bales. Mills demanded consistent supply, and supply began to shape lives and landscapes. In the mill, the effect was immediate. Machines that spun and wove could now be fed without pauses, and output soared. The technology also carried a darker weight, because increased demand for cotton was tied to harsh labor systems in many places. The machinery was brilliant, but its consequences were tangled. It reminds us that a machine can amplify whatever society already is, for better and for worse. Cotton preparation technology turned fiber into an industrial river, and it kept the looms hungry. The spinning mule stretched fibers into thread with practiced motion. The spinning mule earned its name because it combined ideas from earlier spinning systems into something stubbornly effective. It worked by drawing out fibers into a thinner strand, then twisting that strand into strong thread and winding it onto spindles in a repeating cycle. The key was control. Too little twist, and the thread broke. Too much, and it kinked and weakened. Operators learned to read tension like musicians read tempo, and they adjusted the machine to match different fibers and desired qualities. The mule could produce fine yarn suitable for delicate cloth, and it could do so in large quantities. That combination helped make textiles both abundant and varied. It also changed who could buy what. Fabrics that had once been expensive became more common, and wardrobes expanded across social classes. The mule was not only a factory tool. It was a tastemaker because it influenced what kinds of cloth were possible at scale. When thread becomes reliable, designers dare to dream. The spinning mule turned softness into precision, and precision into everyday material life. Power looms wove cloth faster than hands could ever follow. Weaving by hand is a dance of coordination, shuttle, beat, and pattern, repeated until a bolt of cloth finally appears. The power loom took that dance and gave it an engine. Mechanized shuttles, harnesses, and beaters moved with timed force, and the loom could maintain speed hour after hour. That speed changed the marketplace. Cloth became cheaper, and fashion cycles accelerated because production could respond more quickly to demand. Inside the mill, the loom reshaped labor. A single worker could oversee multiple looms, listening for the snap of a broken thread and watching for flaws that could ruin yards of fabric. Noise became constant. Safety became urgent because moving parts did not pause for tired fingers. The loom also pushed technical innovation. Better gears, smoother cams, and stronger frames were needed to reduce vibration and improve reliability. This was not only cloth making. It was a machine teaching industry how to coordinate many motions at once. When you watch a loom run, you see the Victorian era's belief that rhythm can be engineered, and that engineering can multiply output without mercy. Jacquard cards let looms remember patterns, like early machine code. A patterned fabric looks effortless when it hangs in a shop window, but creating it by hand once demanded intense concentration. Jacquard cards changed that by turning pattern into punched instructions. Each card carried holes in specific positions. Needles either passed through or were blocked, and that choice decided which threads lifted on each pass. A chain of cards became a stored program, and the loom followed it faithfully. The astonishing part is not only the beauty of the result. It is the idea that a machine could be guided by abstract information. Patterns could be copied, shared, and improved without teaching every weaver the same complex sequence. Designers gained freedom, and mills gained repeatability. Workers gained a new relationship with skill, because the pattern lived in the cards as much as in the hands. Long before electronic computers, this system showed how decisions could be encoded, then replayed. Cloth became a kind of memory, and the loom became a reader. Victorian factories used line shafts, sending power through spinning belts. Walk into a 19th-century workshop and look up. You might see a forest of shafts turning along the ceiling, driven by a single engine in another room. From those shafts, belts dropped down to each machine like loops of moving leather. One power source could run an entire floor. That arrangement was efficient, but it shaped factory life in strange ways. Machines had to be placed where the belts could reach, so the building itself became part of the system. Starting and stopping power was a physical act. A belt could be shifted from a loose pulley to a tight one, and a machine would wake up. The belts also carried danger. A loose sleeve or a careless hand could be pulled in before anyone could react. Yet the sight was mesmerizing. A whole room sharing motion, as if it were breathing together. Line shafts turned factories into coordinated organisms, where one heartbeat powered many limbs, and productivity depended on alignment and tension as ken, much as on human effort. The flywheel stored energy, smoothing machines through hard moments. Many machines face a problem that is easy to miss. The load is not constant. A press meets resistance at one point, a pump strains at another, and an engine's pistons deliver power in pulses rather than a steady stream. The flywheel answered with inertia. By spinning a heavy wheel, a machine could store energy when work was light, then release it when work suddenly demanded more. That made motion smoother, and smooth motion meant fewer broken parts and better results. In a textile mill, steadier rotation could reduce thread breakage. In a workshop, it could keep cutting tools from chattering. The flywheel also made engines feel calmer. Instead of jerking and surging, the machine carried itself through the cycle with confidence. People sometimes described large flywheels with awe because they seemed to hold time inside their rim. Once a flywheel was moving, it was not eager to stop. That stubbornness was useful. It turned uneven power into dependable rhythm, and it helped Victorian machinery behave like a steady partner. Governors held engine speed steady, even when loads changed suddenly. A steam engine can race when the load drops, and it can sag when the load rises. Neither is welcome. Overspeed can destroy machinery, and underspeed can stall production. The governor was a clever mechanical judge that watched speed and responded without human hands. Often it took the form of spinning balls that rose outward as rotation increased, then dropped inward as it slowed. That movement controlled a valve, which adjusted steam input and stabilized the engine. The beauty is that it feels almost alive. The machine notices its own state, then corrects itself. In factories, that stability mattered for quality. Looms needed consistent speed. Pumps needed reliable strokes. Generators needed steady rotation to produce usable electricity. The governor also changed trust. Owners could run more complex systems because one part was watching another. It is easy to overlook this as a detail, but it is a turning point. The governor is a sign that Victorian machines were beginning to regulate themselves, and that idea leads straight toward modern control systems. Lubrication became a science because friction ate profit. When a machine runs, friction is always negotiating. It steals energy as heat, it grinds surfaces into dust, and it shortens the life of expensive parts. Victorian industry learned that oil was not a luxury. It was a necessity with financial consequences. A well-lubricated bearing could run cooler, last longer, and waste less power, and those savings multiplied across a factory full of shafts and gears. The challenge was choosing the right lubricant, delivering it reliably, and keeping dirt out. Too little oil could seize a machine. Too much could attract grit and turn into abrasive paste. Engineers began to think about viscosity, temperature, and material compatibility, even if they did not always use modern terms. Oil cups, wicks, and drip feed systems appeared, and maintenance schedules became part of production planning. This is one of the quiet stories of the era. Big machines get the glory, but small choices keep them alive. Lubrication turned motion from a short-lived spectacle into a dependable habit, and it helped industry scale without constant breakdown. Water wheels still mattered, especially where rivers were reliable. Even in the age of coal and steam, running water could be a gift. A good river provides power without fuel deliveries, and without boilers that demand careful watching. Many mills continued to rely on water wheels, and new designs made them more efficient. Overshot wheels took advantage of height. Water fell into buckets near the top, and gravity did much of the work. In other places, turbines began to replace wheels, turning water into smoother rotation. Water power shaped landscapes. Mills clustered along streams. Dams and weirs altered flow. Communities grew around dependable energy, and that energy could be quieter than steam, yet just as productive. The limit was geography. Drought could slow a mill, and floods could damage equipment, so owners balanced risk against cost. Still, water wheels remind us that Victorian technology was not a single straight path. It was a patchwork of solutions, chosen for local needs. In some valleys, the future still turned on a river, and it turned day after day without smoke. Steam turbines arrived late, hinting at a new electric century. A piston engine moves in steps. Push, pause, return, repeat. A steam turbine offered something smoother. Steam rushed through rows of blades and made a shaft spin rapidly, like wind turning a pinwheel, but with far more force. This approach reduced vibration, and it could reach high speeds that suited electrical generation. It arrived late in the Victorian era, but its timing mattered. Cities were starting to crave electricity for lighting, traction, and industry, and turbines promised large-scale power in a more compact form. The change also shifted the skill set of engineering. Precision blades, careful balancing, and high-speed bearings became crucial. The turbine feels like a bridge between worlds. It still depends on boiling water and managing steam, yet it points towards centralized power stations feeding networks of wires. In a sense, it was steam learning a new language, the language of rotation made for generators. The turbine suggested that the age of smoke could evolve into an age of current, and that progress could come from making motion smoother rather than merely stronger. Gas lighting used networks of pipes, turning cities into glowing grids. Before electric light spread, many cities learned to manufacture illumination from coal gas. Gasworks heated coal in sealed vessels, drew off the gas, cleaned it, and sent it through underground mains. Street lamps then turned that flow into flame, and flame into a new urban night. The transformation was social. Shops stayed open later. Streets felt safer for pedestrians. Entertainment expanded beyond daylight hours. Gas also created new kinds of work. Lamplighters walked their routes, igniting and extinguishing lights and maintaining the burners. The system brought hazards too. Leaks could cause explosions, and poorly vented interiors could lead to sickness, so regulation and engineering had to mature quickly. Yet the infrastructure itself was astonishing. Miles of buried pipe, pressure management, and metering turned light into a service, not a one-off household act. Gas lighting taught cities how to operate networks, where a centralized plant could feed thousands of points at once. It was a rehearsal for modern utilities, and it made the night feel planned. Electric arc lamps lit streets harshly, before gentler bulbs won. The arc lamp was not a subtle invention. It produced a brilliant, intense light by creating an electric arc between carbon electrodes. Outdoors, that brightness could be thrilling. A street corner could suddenly look like midday, and crowds gathered to watch the unfamiliar glare. Yet the light could also be unpleasant. It cast sharp shadows. It could flicker, and it often suited wide spaces more than cozy rooms. Arc lamps found roles in public squares, factories, and large halls where sheer illumination mattered. They also came with practical challenges. The carbon rods burned down and needed adjustment, and the electrical systems behind them were still new and sometimes unreliable. Even so, the arc lamp was a public announcement. Electricity was no longer only a scientific curiosity. It was a civic spectacle, and it changed expectations overnight. Once people had seen streets lit without flame, the idea could not be unseen. The arc lamp opened the door, even if it was too loud in its brilliance to feel like home. The incandescent lamp made light personal, not just public. Where arc lamps overwhelmed, incandescent bulbs invited. A thin filament heated until it glowed, sealed inside a glass bulb, could provide steady light without soot, smoke, or an open flame. That difference changed interiors. Reading became easier in the evening. Homes could be lit room by room, with switches that felt almost magical in their simplicity. Businesses benefited too. Stores could display goods with consistent light, and offices could work after sunset without the constant attention that gas flames required. The change was not only comfort, it was safety. Fewer open flames meant fewer accidental fires, especially in crowded districts filled with wood and fabric. Electric lighting also encouraged new habits. People began to expect reliable brightness on demand, and that expectation pushed power generation and wiring to expand. The bulb made electricity intimate. It was no longer a distant marvel in a laboratory or a blazing streetlight. It became a quiet companion over a table, shaping evenings and extending the day. In doing so, it helped shift the Victorian world toward modern life, one glowing filament at a time. The telephone carried voices by wire, and business learned to talk. For generations, long-distance communication meant writing, sealing, and waiting. The telephone replaced that pause with presence. A voice could travel along a wire, change into electrical variations, then become sound again at the other end. The effect was startling. Decisions that once took days could happen in minutes, and misunderstandings could be corrected in real time. Businesses adapted quickly. Orders could be confirmed, shipments redirected, and crises managed without sending a messenger through rain and traffic. Yet the change was also personal. A familiar voice could cross a city without needing a visit, and that felt like a new kind of closeness. The system demanded infrastructure, poles, cables, and reliable exchanges, and it also demanded etiquette because talking through a device was a new social act. Early lines could be noisy, and connections could fail, but the expectation had been set. Once people experienced conversation at a distance, silence began to feel like a choice, not a limit. Switchboards turned operators into human routers of conversation. A telephone call did not simply happen. In many places, it was built by a person. At the exchange, an operator sat before a switchboard filled with jacks, cords, and small signals. A light blinked. A voice asked for a number. With practiced speed, the operator connected one line to another, creating a temporary path for two strangers to speak. This was skilled work. It demanded quick memory, patience, and calm under pressure, when multiple lines demanded attention at once. The switchboard also made the network feel social. The exchange was a listening center for a town's daily life, even with rules meant to protect privacy. For many women, this role offered wage work and a respected position, though it could be exhausting and tightly managed. The physical act of plugging and unplugging turned abstract connectivity into something you could see and hear. Each click was a little bridge. Each cord was a reminder that communication was not yet automatic. It was organized by human hands, and that human layer shaped the experience of early telephony. The phonograph trapped sound in grooves and replayed a living moment. To Victorian ears, the first playback could feel like a ghost had learned to speak. The phonograph worked by turning sound waves into motion, then carving that motion into a surface as a repeating pattern. Later, a needle traced the groove and recreated the vibrations, bringing a voice back into the room. That idea is profound. It means time can be folded, because something said once can be heard again. People used it for music, speeches, and novelty. But the deeper change was psychological. Performance no longer needed the performer present. A singer could be heard miles away, long after the last note had been sung. This created new kinds of fame and new markets for entertainment. It also raised new questions. Whose voice is it once it can be copied? What does it mean to own a performance? Early recordings were scratchy, and the machines were temperamental, yet they revealed a future where memory could be mechanical. The phonograph made sound collectible, and that made everyday life feel newly recordable. Early motion cameras made time visible, frame by frame. Victorians lived in a world of still images. Then cameras began to capture sequences, and movement became something you could study. Early systems took rapid snapshots on film, each one a slice of a moment. When projected in quick succession, the mind stitched them into motion, and a new medium was born. The first audiences were often astonished because the effect was more than a trick. It showed ordinary actions, a horse running, a worker hammering, a train arriving, as if reality had been bottled. Scientists and artists both saw potential. Motion studies could reveal patterns too fast for the eye, and filmmakers could stage scenes that felt like waking dreams. This technology also changed how people imagined history. A moment could be preserved not only as words or paintings, but as moving evidence. Early cameras needed bright light and careful cranking, so the process was demanding. Yet the promise was clear. If you can capture movement, you can preserve behavior, and behavior is where life truly happens. Motion cameras turned time into a strip you could unroll, and that idea still shapes how we remember the past. Photography married chemistry and optics, and portraits became democratic. A painted portrait was once a luxury, and it often showed an idealized version of a person. Photography offered a different bargain. Light passed through a lens, fell onto a chemically prepared surface, and left behind an image formed by physics rather than flattery. The change was social. Ordinary families could afford portraits, and they began to keep faces in drawers, albums, and lockets. The camera also affected status. A worker in plain clothes could be pictured with the same seriousness as a wealthy merchant, and that seriousness mattered. Studios developed their own rituals, including careful poses, headrests to prevent blur, and long exposures that demanded stillness. People learned to manage their expression because a photograph feels permanent in a way a mirror does not. Photography also became evidence. It documented buildings, disasters, distant places, and scientific subjects, and it shaped what the public believed. The medium was not neutral, but it felt authoritative. In the Victorian era, chemistry and glass helped turn identity into an image, and images into a shared currency. The stereoscope created depth from paper and delighted Victorian parlours. A stereoscope could make a flat photograph feel like a window. It used two nearly identical images taken from slightly different angles, one for each eye. When viewed through lenses, the brain combined them into a single scene with convincing depth. In parlours, this was both entertainment and travel. People could experience mountain passes, grand buildings, and faraway streets without leaving their chairs. The sensation could be startling because it invited the body to lean forward as if space were real. The stereoscope also trained visual habits. It encouraged people to think in 3 dimensions and to crave realism in images. Publishers built entire businesses around producing stereoscopic views, and collections became a form of status and curiosity. The device was simple, yet it hinted at later technologies that play with perception, from cinema to modern virtual reality. It also reminds us that Victorian fascination was not only industrial, it was psychological. The stereoscope turned optics into wonder, and it made the mind itself part of the machine. When depth appears from paper, you feel the brain doing work you cannot see, and that is its own kind of magic. Typewriters standardized handwriting, and offices became louder and faster. A handwritten letter carries personality, but it also carries ambiguity. The typewriter offered a new clarity. Each key struck a ribbon and pressed inked characters onto paper, producing text that looked the same no matter who wrote it. That uniformity changed offices. Documents became easier to read, easier to file, and easier to duplicate. It also changed pace. Typing could outrun careful penmanship, and businesses began to expect more correspondence in less time. The sound became part of the culture. Keys clicked, carriage returns snapped, and work gained a steady mechanical rhythm. This tool also reshaped roles. Typing became a specialized skill, and training schools appeared. For many women, typewriting opened a path into clerical work, though it also brought strict supervision and repetitive strain. The typewriter affected language in subtle ways too. Errors were harder to hide, and revisions required planning, so writers learned to think ahead. In a sense, it made words feel manufactured. The typewriter did not only change writing, it changed what organizations believed writing could do and how quickly it should happen. Carbon paper duplicated text long before copiers existed. Imagine writing a letter and creating several copies at the same time without printing presses or photography. Carbon paper made that possible. A thin sheet coated with pigment was placed between pages, and the pressure of typing transferred a shadow of each letter onto the page below. This simple trick changed administration. Contracts could be produced in sets. Receipts could have matching records. Shipping forms could travel with goods while another copy stayed in the office. It reduced disputes because what one person signed could be compared against another copy that matched line for line. Carbon paper also shaped habits. People learned to align stacks carefully, to strike keys with consistent force, and to keep track of multiple pages at once. A smudged copy could become a problem, so neatness became procedural. The technology feels humble, but it multiplied paperwork at the exact moment that businesses and governments were growing more complex. It is easy to picture great inventions as loud and dramatic. Carbon paper was quiet, yet it helped build the bureaucratic muscles of the modern world. It turned a single act of writing into a small production run, and it did it with nothing more than pressure and pigment. The cash register fought theft with bells, drawers, and visible totals. Retail once relied heavily on trust, and trust can be strained when money changes hands all day. The cash register introduced accountability in a form that was hard to ignore. When a sale was entered, the machine recorded the amount, rang a bell, and opened the locked drawer. That sound was not decoration. It signaled that a transaction had been logged, and it made quiet pocketing harder. Many registers also displayed totals, which gave both clerk and customer a shared view of the sale. The result was behavioral. Shop owners gained confidence to delegate, and clerks learned that their work was being counted. The machine also influenced customer experience. A crisp printed receipt felt official, and the ritual of the drawer and bell made the exchange feel standardized. Cash registers became ornate in design, partly because stores wanted them visible, like a symbol of modern management. This is a machine that did not move goods or power factories. It moved honesty into a mechanical routine. It turned commerce into something that could be audited, and that changed how businesses grew. Mechanical adding machines made accounting a crank-turning certainty. Before electronic calculators, numbers had to be managed by handwriting and mental endurance. Mechanical adding machines offered a different kind of confidence. Keys represented values. A crank advanced internal gears, and the total appeared in a window with reassuring clarity. This reduced error, and it reduced fatigue, which matters when a ledger includes thousands of entries. Businesses discovered that better arithmetic could change decisions. Costs could be tracked more accurately. Profits could be understood sooner. Complex operations could be managed with less guesswork. The machines also influenced office culture. Accounting became more procedural, more standardized, and easier to scale, because one person could process more work in the same time. Yet these devices were not magical. They required careful use, and operators had to understand how carries and resets worked, or mistakes could still slip in. Even so, the feeling was powerful. Turning a crank and watching a total update makes abstraction physical. It is a reminder that numbers govern real choices, and that machines can make those choices feel sharper. In the Victorian office, the adding machine turned arithmetic into a mechanism, and that mechanism helped build modern finance. Pneumatic tube systems fired messages through buildings like breath. In a busy office or department store, speed mattered long before email existed. Pneumatic tubes answered with a kind of indoor lightning. A clerk placed a note, cash, or a small document into a capsule, sealed it, then dropped it into a tube. With a hiss of air pressure, the capsule shot through hidden channels and arrived at a distant desk in moments. The system made large buildings feel smaller, because messages did not need a runner weaving through crowds and staircases. It also changed routine. Central cashier stations could serve many counters. Banks could move paperwork quickly between departments. Hospitals could send urgent slips without delay. The sound became familiar, that soft rush followed by a thump as the capsule arrived. Behind the scenes, blows, valves, and switches managed traffic like a miniature railway network. It was both practical and theatrical. A building seemed alive, with arteries carrying information. Pneumatic tubes did not only move objects, they moved expectation toward a world where waiting felt unnecessary. Vacuum pumps enabled science and also powered strange industrial tricks. A vacuum is not nothing. It is a tool that reveals how much air usually does for free. Victorian vacuum pumps pulled gases from vessels, allowing experiments that could not happen in ordinary atmosphere. Electricity behaved differently. Light behaved differently. Materials could be tested without the cushioning presence of air. Those discoveries spilled into industry. Reduced pressure helped with processes that needed evaporation at lower temperatures. It improved certain forms of sealing and testing, where leaks could be detected by changes in pressure. It even enabled gripping devices, where suction could hold smooth surfaces long enough to lift or move them. The pump itself demanded craft. Valves had to seal, pistons had to fit, and lubricants had to behave under unusual conditions. When the machine ran well, it seemed to create an invisible force, pulling on the world by removing what was in the way. A vacuum pump teaches a fascinating lesson. Sometimes the best way to gain power is to take something away, and then watch what becomes possible. The barometer and recorder instruments made weather a measured story. Weather once felt like a mood of the sky, unpredictable and personal. Victorian instruments began to make it legible. A barometer tracked air pressure, which often shifts before storms and settles during calmer spells. Add recording devices, and those measurements could be written automatically as lines on paper, hour by hour, day by day. Suddenly, weather had a memory. Patterns could be compared across weeks and seasons. A storm was no longer only a dramatic event. It became data that could be studied, argued over, and used for planning. Shipping and agriculture both had reasons to care, because forecasts can save cargo and harvests. Even city life changed. Newspapers could report conditions with numbers, not just adjectives. The act of measurement also shaped belief. When people see a needle falling before a gale, the world feels less arbitrary. Victorian meteorology was not perfect, but it was transformative. It suggested that the atmosphere could be understood with patience and instruments, and that understanding could reduce fear. Turning the sky into a chart is a quiet kind of power. The anemometer turned invisible wind into counted turns. Wind is felt on the skin, but it is difficult to describe precisely. The anemometer made it countable. With cups that spun in the breeze, or vanes that responded to flow, the instrument converted gusts into rotations that could be recorded. That mattered because wind affects everything from construction to sailing to early aviation dreams. If you want to build higher, you need to know what forces will push your structure. If you want to predict storms, you need more than a glance at clouds. Once wind could be measured, it could be compared between places, seasons, and heights above the ground. Observatories began to gather numbers, and engineers began to use them. The anemometer also changed imagination. It suggested that even something as fleeting as a gust has a pattern, and patterns can be learned. People started to talk about the weather with a new seriousness, as if the air were a machine with settings. A spinning cup on a rooftop may look simple, yet it represents a bold idea. The unseen can be quantified, and once it is quantified, it can be planned for. The electric telegraph needed repeaters because distance weakened messages. A telegraph signal is a pulse, and pulses fade as they travel through long lines. Resistance steals strength. Noise creeps in. The farther the message went, the more it risked arriving as a faint whisper instead of a clear click. Repeaters solved this by listening and resending, restoring the signal so it could keep moving. That created a new kind of infrastructure, not only poles and wire, but intermediate stations and devices that supported communication like stepping stones across a river. Repeaters also introduced trust. A message could pass through many hands and many machines, and it needed to remain accurate. Operators became guardians of clarity, trained to recognize errors and confirm content. The network began to feel like a living system with weak points and repairs, and that made it more resilient. Repeaters quietly expanded the practical range of telegraphy, and that expansion changed commerce, diplomacy, and family news. A short code could cross a continent because someone built places for the signal to catch its breath. In the Victorian imagination, the world grew smaller not only because of wires, but because of the invisible care taken to keep those wires speaking. Submarine telegraph cables demanded insulation that seawater could not defeat. Sending a message under the sea sounds romantic, until you remember what seawater does to metal and electricity. A submarine cable had to survive pressure, abrasion, and constant exposure to salt. Insulation became the heroic material problem. The cable needed a core that carried current, a protective layer that resisted water, and outer armoring that could endure dragging across rocks and sand. Early cable makers learned through failure, because a single flaw could flood the insulation and silence the line. They tested materials, improved manufacturing, and developed techniques to seal joints with care, since the ocean does not forgive sloppy workmanship. Laying the cable was only the beginning. Repair meant locating a break somewhere in vast darkness, hauling the line up, and splicing it under difficult conditions. Yet when it worked, the effect was astonishing. A continent could speak to another without waiting for ships. Submarine cables turned oceans from barriers into conduits, and that shift made diplomacy and trade more immediate, for better and for worse. A cable on the seabed is easy to forget. It is also one of the boldest acts of Victorian engineering, because it asks the sea to host human communication. Cable-laying ships worked like floating factories, paying out lifelines. A cable-laying ship carried miles of coiled cable in its hold, arranged so it could feed out smoothly without tangling. On deck, large drums and braking systems controlled tension, because too much pull could snap the line, and too little could leave loops that would chafe on the seabed. The work demanded constant attention. Crews monitored weather, currents, and the ship's speed, because the cable had to settle gently into place. When a fault occurred, the ship became a workshop at sea. Grappling hooks searched for the lost end, and once it was hauled up, the splice had to be done with meticulous care. Every join was a potential weakness, so craftsmanship mattered as much as seamanship. These ships were not glamorous passenger vessels. They were purpose-built machines, combining navigation with industrial handling. Their success could connect empires, enable faster news, and reshape economics. When a cable ship moved slowly across the ocean, paying out its line, it was laying down something more than metal and insulation. It was laying a promise that distance would be less powerful tomorrow than it was today. The postal sorting machine era began slowly, but urgency was rising. Victorian mail systems carried the weight of modern life: bills, love letters, legal notices, and business orders. As cities grew, hand sorting alone struggled to keep pace. Early sorting machines and mechanized aids began to appear, and even small improvements mattered. Conveyors could move bundles. Cancelling devices could stamp marks rapidly. Systems were designed to reduce handling time and prevent misroutes that could ruin deadlines. The larger story is the rising expectation of speed. People began to plan around the mail, trusting that a letter would arrive within a predictable window. That trust encouraged more correspondence, which created even more pressure on the system. Postal work became highly organized, with shifts, routes, and procedures, but treated paper like a circulating bloodstream. Machines did not replace human judgment overnight, but they changed the scale of what was possible. A city could receive and send an enormous volume of communication and still maintain order. When you think about it, that is astonishing. A society that can move millions of small messages reliably can coordinate itself in new ways. The early postal machines were not flashy, but they helped make the Victorian world feel connected, accountable, and fast. Clockwork timers and regulators disciplined factories into synchronized motion. A factory is not only a place with machines, it is a place where machines must cooperate. Clockwork timers and regulators helped impose that cooperation. Bells could ring to start shifts. Time devices could control processes that needed precise intervals, such as heating, drying, or chemical steps. Regulators could keep mechanisms operating at consistent rates, reducing variation that would otherwise spoil quality. This introduced a new form of discipline. Workers adjusted their days to signals that came from gears and springs. Managers learned to think in cycles, quotas, and schedules. Even maintenance became routinized, because a machine that is expected to run all day must be cared for systematically. The psychology shifted too. When time is measured tightly, productivity becomes a number, and numbers invite comparison. This could drive improvement, but it could also create pressure and fatigue. The Victorian era is often remembered for dramatic inventions, yet this quieter change may be just as important. It made time into infrastructure. It turned motion into a coordinated plan, and it trained industry to treat minutes as material. Once a factory runs by clockwork, the idea of unscheduled work begins to feel almost impossible. Hydraulic city systems powered lifts, cranes, and theatre curtains. Some Victorian cities experimented with a fascinating idea. Instead of sending power as spinning shafts or individual engines, they sent it as pressurized water through pipes. A central pumping station forced water into an accumulator, often a tall weighted tower. Then that pressure could be tapped across a district. Buildings used it to run goods lifts, dock cranes, and machinery that needed strong, steady force without smoke indoors. The magic was in the convenience. You could install a compact hydraulic motor and let the city do the heavy work of generating pressure. It also changed public spaces. In theatres, hydraulic power could raise scenery, move curtains, and shift platforms with smooth control, turning stagecraft into engineering. The system demanded careful maintenance because leaks waste power and damage foundations. Pipes had to endure pressure day after day. Yet when it worked, it felt like a utility for motion, as practical as gas and as surprising as electricity. It was a brief glimpse of a city that could deliver strength through a valve. The passenger elevator made upper floors desirable, not dreaded. Stairs once set the value of a building. The higher you lived, the cheaper the rent, because climbing every day was tiring and slow. The passenger elevator flipped that logic. A controlled lift could carry people upward with less effort, which turned height into a luxury instead of a penalty. Views, fresh air, and distance from street noise became attractive, and developers began to build taller because the climb no longer limited occupancy. The elevator also reshaped trust. You had to step into a box, toes a gate, and believe that cables, brakes, and operators would behave. Early systems learned from accidents, and safety devices became central to design, especially reliable brakes that could engage if a cable failed. In hotels and department stores, elevators changed the flow of crowds. People could move vertically like water through a pipe, and that made multi-floor shopping and modern offices feel natural. The elevator did not only lift bodies, it lifted architecture, economics, and the very idea of what a city could become. Steam heating spread warmth through pipes, making winters feel different. Before central heating, warmth gathered near a fireplace and faded quickly across a room. Steam heating offered a different experience. A boiler could send hot steam through pipes to radiators, and those radiators could release heat evenly into multiple rooms. Whole buildings began to feel consistently habitable, not only the one room with the fire. This mattered for comfort, but it also mattered for health and productivity. Schools, offices, and hospitals could keep steadier indoor temperatures, which reduced the daily struggle against cold, damp air. The system demanded engineering. Pipes needed proper slopes for condensate return. Valves needed to control flow without noisy banging. Boilers needed careful attention because pressure is unforgiving. Yet when installed well, steam heat changed habits. People could gather in larger spaces in winter. Work could continue more comfortably after dark. Even clothing choices shifted because indoor life was warmer. Steam heating is one of those inventions that quietly transforms daily experience. It makes a season feel shorter, and it makes a building feel like a shelter designed with intention. Ventilation fans fought smoke and sickness in crowded rooms. Victorian cities packed people into factories, schools, and tenements, and stale air could become a slow threat. Ventilation fans offered a mechanical answer. By pulling in fresh air and pushing out used air, they reduced smoke, heat, and odors that would otherwise linger. In some settings, ventilation was not only comfort, it was survival. Boiler rooms, mines, and crowded workshops could accumulate dangerous gases, and airflow could prevent disaster. Hospitals and public buildings began to take ventilation seriously because fresh air was linked to healthier outcomes, even before every detail of germs was understood. Fans also reshaped architecture. Ducts, vents, and shafts became part of design, and windows were no longer the only strategy. The machines themselves were varied. Some were powered by steam engines, others by belts, and later by electric motors. What unites them is the idea that air can be managed like water. It can be directed, measured, and improved. A ventilation fan is not glamorous, yet it represents a city learning to care for invisible conditions and to treat breathing space as a built service. Refrigeration began with ice machines and changed food and medicine. Victorians knew ice was valuable, but natural ice depends on climate and season. Ice machines began to manufacture cold, and that changed what could be stored, shipped, and trusted. Food lasted longer. Meat and dairy could travel farther with less spoilage. Restaurants and markets could offer items that once vanished quickly in warm weather. The medical implications were equally important. Some medicines and biological materials needed cool storage to remain effective, and hospitals benefited from more reliable temperature control. Early refrigeration systems were complex and sometimes risky, involving compressed gases and careful sealing, so skilled operators mattered. Yet the principle was powerful. Cold became something you could produce on demand, like steam power in reverse. That shifted expectations. People began to think of freshness as manageable, not merely lucky. Refrigeration also changed trade patterns by supporting longer supply chains, and it helped cities feed themselves more consistently. It is easy to focus on engines and rails, but manufactured cold is just as revolutionary. It turns time into something you can slow down, at least for food and medicine, and it makes modern life possible in ways we often forget. Pasteurization relied on control of heat, not a new ingredient. The most elegant solutions can look almost too simple. Pasteurization did not add chemicals, and it did not depend on exotic machinery. It relied on heating a liquid to a specific temperature for a set time, then cooling it, so harmful microbes were reduced without ruining the product. This mattered for milk, beer, and wine, and it mattered for public health. Contaminated milk in crowded cities could spread disease quickly, and safer processing helped protect children and families. The difficult part was not the concept. It was consistency. You needed thermometers you could trust, vessels that heated evenly, and procedures that workers followed every time. That brought industrial discipline into kitchens, dairies, and breweries. It also changed the relationship between science and everyday consumption. Invisible organisms became part of the story of what you drink, and that idea encouraged sanitation improvements across the supply chain. Pasteurization is a Victorian reminder that modernity is not always a louder machine. Sometimes it is a better rule applied with care, using heat as a tool of protection. The safety lamp protected miners by taming flame behind mesh. In coal mines, light was necessary, but open flame could be deadly. Gases such as methane might collect in pockets, and one spark could ignite an explosion that raced through tunnels. The safety lamp addressed this with a deceptively simple barrier. A fine metal mesh surrounded the flame, allowing light and air through while cooling the hot gases enough to prevent ignition outside the lamp. This let miners see without turning their lamps into detonators, at least under safer conditions. The lamp also became an early warning tool. In certain designs, the flame's behavior could hint at dangerous gas levels, giving workers time to retreat. Yet it was not a guarantee. Poor maintenance, damaged mesh, or reckless use could still lead to tragedy. That tension shaped mining culture, mixing confidence with constant vigilance. The safety lamp represents a fascinating Victorian theme. Engineering was being asked to negotiate with invisible threats and to create safety through understanding of heat and airflow. A small lamp could mean the difference between a working shift and a catastrophe, and that made it one of the era's most important machines. Steam fire engines turned emergencies into battles with pressure. A city fire spreads fast when buildings are packed close together. Before powered pumping, firefighters depended heavily on muscle and hand pumps, which could be overwhelmed by a major blaze. Steam fire engines brought a new kind of force to the scene. A boiler powered a pump that could deliver water at higher pressure and in greater volume, helping crews reach upper floors and fight stronger flames. The arrival of such a machine could change morale. It signaled that the city was bringing industry to defend itself. It also demanded coordination. The engine needed fuel, water supply, and setup time, and crews had to manage hoses, nozzles, and the risks of steam under stress. Over time, fire brigades became more professional, with drills, stations, and improved hydrant networks to support rapid response. The steam fire engine is compelling because it shows technology meeting crisis. It turns a chaotic event into a contest that can be planned for, practiced for, and sometimes won. When a steam pump roared into action, it did more than spray water. It made cities more resilient, and it changed how people imagined public protection. Waterworks used pumps and reservoirs, giving cities steady, clean supply. A growing city cannot rely on wells and chance. It needs a system. Victorian waterworks built that system with intake points, filtration in some places, pumping stations, and reservoirs that stored supply for daily peaks and emergencies. The pumps were often impressive machines housed in grand buildings because clean water was a civic priority worth displaying. A steady supply changed everything. Homes could have more reliable taps. Street cleaning improved. Firefighting gained stronger hydrant pressure. Public fountains became possible, and industries that needed large volumes of water could operate more predictably. The health effects were profound when water sources were protected and distribution was maintained properly. Yet the system also created new responsibilities. Pipes could leak and contaminate. Reservoirs needed protection. Pressure management had to be stable. Waterworks taught cities to think like engineers. They had to plan for population growth, seasonal changes, and infrastructure renewal. It is easy to forget how revolutionary this was. A clean, reliable supply is not just convenience. It is the foundation for modern urban life, and Victorian machines built that foundation one pump stroke at a time. Gas meters measured usage and turned light into a bill. When gas lighting spread, it created a new question. How do you charge fairly for something invisible flowing through a pipe? Gas meters answered with mechanical honesty. As gas passed through, it moved chambers or diaphragms inside the meter, and those movements advanced a counter. Suddenly, illumination could be quantified. That shifted behavior. Households and businesses began to consider how many lamps they used and for how long, because usage now had a measurable cost. Utilities gained a way to fund expansion, maintain pipes, and stabilize supply, which helped networks grow more reliable. The meter also changed trust between customer and company, because disputes could be argued with numbers rather than accusations. Yet it introduced new anxieties too. A glowing room could feel luxurious, but it could also feel expensive. This is a classic Victorian pattern. Technology spreads, then measurement follows, then society reorganizes around the measurement. The gas meter made the night an itemized service. It turned brightness into consumption, and consumption into a relationship between private life and infrastructure. The electric motor reversed the dynamo, turning current into motion. Once people learned that spinning coils could generate electricity, someone asked the mirror question. What if electricity could make coils spin? The motor answered with silent confidence. Feed current into a magnetic field, and torque appears as if from nowhere, turning a shaft that can drive belts, fans, and tools. This was liberating because it separated power from smoke. A workshop no longer needed a boiler in the yard or a line shaft overhead. A motor could sit right beside the machine it served and start with a switch. That flexibility changed factory layouts and enabled smaller businesses to mechanize without huge infrastructure. It also invited new inventions, from elevators to pumps to household devices that felt almost magical. Motors demanded good wiring, careful insulation, and reliable supply, so they pulled cities toward better electrical networks. They also taught a new intuition. Invisible current could become visible work, and that conversion could be controlled precisely. The motor made electricity practical not only for light, but for muscle, and it turned energy into a tool that could be placed anywhere. Early power stations were loud, hot rooms filled with spinning danger. A Victorian power station could feel like stepping into an engine's throat. Dynamos whirred. Belts and shafts spun. Steam engines pounded or turbines hissed, and every surface seemed warm. Operators lived among gauges, switches, and oil, watching for overheating, sparks, and sudden mechanical failure. The air carried the smell of hot metal and insulation, and the floor might tremble with rotation. These stations were not simply buildings. They were new kinds of public organs, created to feed streets and homes with electricity. Their location mattered because transmission over distance was challenging, so stations often rose near the demand, right in the city's fabric. That proximity made the marvel feel immediate. A lamp across town depended on that roaring room. It also made risk immediate. A fault could start a fire, a belt could snap, and an exposed contact could kill. Safety procedures evolved because they had to, and the people who ran these stations became a new profession, half engineer and half guardian. The early power station shows how modern comfort often begins in harsh places, where humans learn to manage powerful systems by attention and discipline. Telegraph relays clicked like insects, translating weak signals into strong ones. Over long distances, a telegraph pulse can arrive tired, too faint to move a sounder clearly. The relay acted like a careful listener. A weak incoming current would energize an electromagnet, which pulled a small armature and closed a separate circuit. That second circuit could send a fresh, strong pulse onward, restoring clarity without changing the message. The result was a chain of communication that could stretch far beyond what one wire segment could handle. Relays also made the network more complex and more fascinating. Each station became a place where invisible signals were handled, checked, and passed along. The sound of operation could be constant, a steady chatter of clicks that made the building feel alive. In large offices, you could almost hear information moving. This had cultural consequences. News could spread faster. Markets could respond faster. Mistakes could spread faster too, so protocols and confirmations became important. The relay is a small device with a big idea. You can extend a system by letting it renew itself along the way, and that principle appears again and again in modern technology. The Wheatstone Bridge made electrical measurement precise and repeatable. Electricity can feel slippery because you cannot see it, and early experiments often relied on guesswork. The Wheatstone Bridge offered a way to measure resistance with confidence, using balance rather than brute force. By arranging resistors in a diamond shape and adjusting values until a detector showed no current in the middle branch, you could determine an unknown resistance from B. Known ones. That moment of balance is elegant. It turns measurement into a quiet proof. This mattered for telegraphy and for manufacturing, because reliable wiring and components require standards. If you can measure resistance accurately, you can detect faults, compare materials, and improve designs systematically. The bridge also shaped scientific culture. It encouraged careful calibration and repeatability, which are the habits that let technology scale. An engineer could say two components match and prove it, not argue it. In a world building, longer cables and larger electrical networks, that ability was essential. The Wheatstone Bridge did not generate power. It generated trust in numbers, and trust is what lets an invisible force become an engineered utility. The galvanometer let scientists see current as a moving needle. Before you can control electricity, you need to know when it is present and how strong it is. The galvanometer made that knowledge visible. A current passing through a coil created a magnetic effect, and that effect moved a needle across a scale. Suddenly, an invisible flow became a physical gesture you could watch. This changed laboratories and workshops alike. Experiments could be compared. Batteries could be tested. Telegraph lines could be checked for faults, because a weak deflection could warn of a break or a leak. The device also trained intuition. People began to think of electricity in degrees, not as a simple on or off. A tiny twitch could matter. A steady deflection could signal stability. In demonstrations, the moving needle became a kind of theater, because it responded instantly to changes that were otherwise mysterious. The galvanometer helped turn electricity from a curiosity into a discipline with instruments, and instruments create confidence. When a needle moves, you feel the world responding to rules, and that feeling can be addictive. The Victorian era learned to trust the needle, and that trust helped build networks that depended on measurement. Steam-powered printing presses fed paper fast, then swallowed ink. A Victorian printing hall could sound like controlled thunder. Steam power drove rollers, gears, and feeders that pulled paper through at a pace no hand press could approach. Ink was spread in thin films, type met paper with repeating force, and sheets emerged in steady streams. Speed changed everything about publishing. Deadlines tightened because you could print later and still distribute widely. Newspapers could grow larger, with more columns and more frequent editions, because the press could keep up. This machinery also demanded a new kind of care. Ink consistency mattered. Paper quality mattered. Alignment mattered, because a small error could waste thousands of sheets. Workers became specialists who understood the press's moods, the way it warmed up, the way it vibrated, the way it jammed. The result was a public that heard more voices more often, and that altered politics, reform movements, and popular culture. A steam press is not only a machine for words. It is a machine that amplifies urgency. It turns information into a flood, and once a flood begins, society learns to swim in it. Linotype arrived late, casting lines of type like molten sentences. Setting type by hand was slow, and it limited how quickly information could spread. Linotype changed the bottleneck by mechanizing composition. An operator pressed keys, and the machine assembled matrices for letters into a line, then poured molten metal to cast that whole line as a single slug. When the line was printed, the matrices could be reused, ready for the next text. This was astonishing in its choreography. Language became a physical process of selection, assembly, casting, and cooling. It also changed labor. Skilled compositors had to adapt, and new operators had to learn a machine that combined keyboarding with mechanical awareness. For newspapers, the impact was immediate. Faster setting meant later news could still make it into print, and editions could expand without impossible overtime. The machine demanded a hot metal system, so safety and ventilation mattered, but the trade was worth it. Linotype helped create the modern news cycle, where speed and volume become expectations. It is a reminder that the way we receive information often depends on tools we never see, and that those tools can reshape public life as powerfully as engines reshape transport. The rotary press made headlines cheap and public opinion louder. A flatbed press works in steps. A rotary press works in flow. By wrapping printing surfaces around cylinders and feeding paper continuously, it could produce enormous quantities quickly. This was perfect for newspapers, which rely on scale. When printing becomes cheaper per copy, circulation can rise, and a publisher can reach people who were previously priced out. That expansion changes society. Shared stories become more common. Political arguments spread faster. Sensational reporting can travel farther, and so can serious investigation. The rotary press also encouraged new distribution systems because stacks of papers had to be moved rapidly to stations, street cellars, and distant towns. The pace of public conversation accelerated. A rumor could be printed in the morning and argued over by lunch, and corrections might struggle to keep up. The machine did not choose the content. It amplified whatever was fed into it. That is why it matters. A rotary press is a technology of attention, and attention is a form of power. By making print abundant, it made influence more contested, and it made public opinion feel like a force that could be steered, provoked, or rallied at scale. Mechanical clocks became factory rulers, not just household ornaments. In a home, a clock can be comforting. In a factory, it can be commanding. Mechanical clocks allowed employers and workers to share a single schedule that did not depend on sunlight or personal judgment. Shift bells and time cards grew from that shared reference. Production could be planned in hours and minutes, and lateness could be quantified without argument. The clock also coordinated machines. Processes that depended on timing, such as heating cycles or staged assembly tasks, could be regulated more reliably when the day itself was standardized. This changed culture. People began to think of time as something you spend, save, and waste, because it could be measured so precisely. It also created tension. A clock does not care if your child is sick or if the streets are muddy. It sets a rhythm that can feel relentless. Yet it enabled new coordination across railways, offices, and factories, and that coordination underpinned industrial scale. The Victorian mechanical clock is a fascinating symbol because it shows how a small device can govern a huge system. It turned minutes into management, and it made punctuality an economic principle. Standardized parts let repairs happen anywhere, not only at the maker. A machine is only as useful as its ability to be kept alive. In earlier eras, a broken part often meant returning to the original workshop or paying for a bespoke replacement shaped by hand. Standardized parts changed that story. If components were made to consistent dimensions, a repair could be a swap rather than a craft project. Railways benefited enormously because locomotives and carriages needed constant maintenance far from where they were built. Factories benefited too, because downtime is expensive and a stockroom of spares can save a day's output. Standardization also created new businesses, suppliers who could make compatible parts for many customers, and that broadened access to machinery. It influenced design philosophy. Engineers began to think in modules and assemblies, which made complex machines easier to build and easier to service. This shift feels practical, but it is deeply transformative. It turns technology into infrastructure. Once parts are standardized, a whole network of workshops can support a machine, and that support makes the machine worth investing in. Reliability is not only about strong materials. It is about systems that allow recovery from failure, and standardized parts made recovery faster, cheaper, and more widespread. The Gatling gun used rotating barrels to multiply firing speed. Victorian inventors often looked at a limitation and asked how to divide it into parts. The Gatling gun applied that mindset to firepower by using multiple barrels arranged around a central axis. As the mechanism rotated, each barrel went through its own cycle of loading, firing, and cooling, which reduced overheating compared to a single barrel working barrel alone. The result was a weapon that could sustain a high rate of fire for its time, powered by a hand crank in many versions. The engineering idea is the key. Instead of making one barrel do everything faster, it shared the work among several, like a factory line in miniature. That approach influenced later designs and changed how militaries thought about supply, training, and battlefield dynamics. Even without focusing on violence, you can see the broader pattern. Mechanization was moving into every domain, and repetition could be amplified by clever motion. The Gatling gun reflects the era's faith that complex tasks could be broken into cycles, then accelerated by machinery. Rifling and machining made weapons more accurate and battles more distant. Older firearms could be unpredictable, especially at longer ranges. Rifling changed that by cutting spiral grooves inside a barrel, which made a projectile spin and fly more steadily. Precision machining made those grooves more consistent, and it improved the fit between parts, which reduced variation from shot to shot. The consequence was not only technical, it changed behavior. If accuracy improves, tactics shift, because distance becomes a factor in planning rather than a barrier to effectiveness. Training changes too. Marksmanship becomes more valuable, and sighting systems receive more attention. Manufacturing changes as well. Standardized components and reliable metallurgy matter more when performance depends on tight tolerances. This story also links back to Victorian industry at large. The same lathes, gauges, and quality control that built engines and railways could also build more precise mechanisms. It is a reminder that tools are rarely confined to one purpose. When a society learns to make metal parts accurately, many fields transform at once. Rifling and machining made accuracy a product, not a lucky outcome. Steam-powered mills produced steel rails, which made trains safer. Rail travel depends on a deceptively simple promise. 2 lines of metal must carry heavy loads at speed, without failing. Steam-powered mills helped keep that promise by producing long, strong rails with more consistency than earlier methods. As railways expanded, demand grew for rails that could resist wear, hold shape, and handle repeated impacts from wheels and brakes. Better rolling processes and stronger steel reduced breakage and deformation, which lowered the risk of derailments and reduced maintenance disruptions. It also allowed heavier trains and more frequent service, because the track could endure more punishment. The improvement was not only in the rail itself. Standardized rail sections made installation and replacement faster, which mattered when a line stretched across vast distances. This is one of those quiet safety stories where metallurgy meets public confidence. Passengers might never see the mill, and they might never think about the rail under them. Yet every smoother journey owed something to the ability to shape steel into reliable lengths again and again, with industrial precision. The Suez Canal relied on dredging machines, not just shovels. Cutting a canal through stubborn earth is not only excavation. It is logistics, persistence, and machinery that can move endless material without tiring. In the Suez Project, dredging machines played a crucial role in removing sediment and widening channels, especially where water and soft ground made traditional digging inefficient. These machines could scoop, lift, and transport spoil continuously, turning a vast landscape task into a repeating mechanical process. The scale was hard to grasp. Every bucket of earth removed had to go somewhere, and the canal's shape had to remain navigable, not merely cut. The payoff was global. A shorter sea route between Europe and Asia changed shipping schedules, fuel needs, and the economics of trade. Ports gained importance, naval planning shifted, and the world felt more connected by a line of water through desert. The canal is often described as a triumph of vision. It was also a triumph of machines built for monotony. Machines that did not mind doing the same hard motion thousands of times until geography itself was a grammar. Edited. Cast iron and steel bridges stretched farther, changing rivers into roads. A river can be a boundary for centuries, until a bridge turns it into a detail. Victorian bridge building advanced rapidly as cast iron and later steel enabled longer spans and stronger structures. Engineers learned to distribute forces through trusses and arches, using geometry as a partner to material strength. New manufacturing methods made large beams and plates available, and improved riveted connections helped frameworks behave as unified systems. These bridges were more than crossings. They were statements of confidence, often placed where older masonry would have been too heavy or too limited. Railways especially benefited because trains demand sturdy, predictable pathways. When a bridge is reliable, commerce flows, travel becomes routine, and communities on opposite banks begin to share daily life. Victorian bridges also invited public attention. People visited them, wrote about them, and treated them as attractions because they looked like ideas made solid. The deeper change was practical. A strong bridge collapses distance by removing delays, ferries, and seasonal hazards. It turns water into a line on a map rather than an obstacle in your day. The Crystal Palace showcased industrial machines like wonders in a temple. When people walked into the Crystal Palace, many felt as if they had entered the future. The building itself was a marvel of glass and iron, and inside it, machinery was displayed with pride. Visitors could see engines, tools, and industrial systems presented not as dirty necessities, but as achievements worth celebrating. This mattered culturally. It framed invention as public spectacle, and it invited ordinary families to feel ownership of progress. Exhibits demonstrated how goods were made, how materials were shaped, and how nations measured themselves through technology. The experience could be overwhelming, because there was so much to see, and so much noise, motion, and novelty. It also shaped ambition. Inventors and manufacturers used exhibitions to attract buyers, investors, and prestige. Ideas spread because people could observe them directly, then imagine improvements. The Crystal Palace helped create a world where technology had a stage, and where innovation became part of entertainment and national identity. It turned machines into conversation pieces, and conversation into momentum. Victorian inventors built calculating engines, chasing automated thought by gears. Long before electronic computers, some Victorian thinkers tried to mechanize calculation itself. They imagined machines that could carry out repeated arithmetic reliably, without fatigue or distraction. The designs relied on gears, cams, and carefully machined parts that represented numbers as positions and rotations. The challenge was enormous. Small errors in alignment could cascade into wrong results, and building thousands of precise components tested the limits of manufacturing. Yet the vision was striking. If a machine can follow rules, then complex work can be broken into steps, and steps can be automated. That idea sits beneath modern computing, even when the mechanisms look different. These engines also forced people to clarify what calculation is. It is procedure, not inspiration. It is a set of operations applied consistently. Victorian calculating machines were often unfinished or difficult to fund, but their influence reached far. They helped turn computation into an engineering problem, and they suggested that information could be processed like material. When gears stand in for thoughts, you begin to see logic as something buildable. Punched card tabulators counted data fast, foreshadowing the information age. As societies grew, they began to drown in paperwork. Counting people, tracking goods, and summarizing results could overwhelm human clerks. Punched card tabulators offered a bold solution. Information was encoded as holes in cards, and the machine read those holes using mechanical and electrical sensing, then sorted and counted at speeds that felt astonishing for the time. The beauty is the abstraction. A hole is not a number by nature, yet it can represent one if everyone agrees on the code. Once that agreement exists, the machine can process facts without understanding them, simply by following physical rules. That separation of meaning from mechanism is powerful. It makes large-scale administration possible, and it also makes mistakes scalable if the encoding is wrong. These systems introduced new jobs, from card punch operators to maintenance technicians, and they encouraged institutions to think in data sets rather than debris, piles of paper. Long before modern computers, punched cards taught the world to treat information as something you can store, move, and compute with. The tabulator was not only fast accounting. It was a new way of seeing society through patterns made of holes. As we come to the end of our journey through the machines of the Victorian era, you can almost feel the world they built still humming in the background. Steam engines turning heat into motion, and pulling mines dry so deeper layers could be reached. Railways stitching towns into a single beating timetable. Factories filling with belts, shafts, and carefully measured parts, where a millimeter of accuracy could decide whether a machine sang or shook itself apart. We drifted through glowing streets, from gas lamps fed by buried pipes to electric light that made night feel newly usable. We listened for the click of telegraph relays and the snap of switchboard cords, as voices and messages began to travel faster than any person could run. We watched paper fly through presses and saw information become something that could be produced at scale. We even brushed past the stranger edges, underwater vessels testing the silence beneath the surface, and punched cards turning human records into patterns AE. Machine could count. If you enjoyed this slow wander through Victorian invention, you might like to tap, like, or subscribe, or leave a small comment about the machine that surprised you most. It helps this channel find other curious minds who also enjoy falling asleep with history. And if you are still awake, there will be another video waiting on screen, ready to carry you onward into the next story. But for now, let the noise of the engines fade. Let the gears and whistles soften in your imagination. Allow your breathing to slow and your thoughts to loosen their grip. You do not need to solve anything. You only need to rest as the century of iron and steam drifts quietly into the distance. Sleep well and good night.